Let me welcome you then, since there is no chair, to this afternoon session. I know that the dessert buffet is very tempting, and that's why perhaps people have moved to another hall instead of this one, but I will start, and then perhaps slowly more people will come. I would like to introduce myself. I'm a medical physicist by training, and I've been working in all aspects of applications of non-ionizing radiation in medicine, and also on non-ionizing radiation safety. So my PhD was on microwave hyperthermia. Then I moved for a while to safety of mobile phones, went back to Erasmus Medical Center under Gerard van Roon, where I worked on quality assurance of superficial hyperthermia. Moved back to Greece, where I did some work again on safety, and since 2012, I have joined a group in our department, which is working on nanoparticle hyperthermia, in fact, magnetic fluid hyperthermia. So I'm not such an old donkey in this field of magnetic fluid hyperthermia, but I have collected more than 5 years of experience in this field. Actually, when we started working on this field, it was immediately after Magforce had managed to get the regulatory permission for their nanotherm, as I will show you later, the nanotherm treatment. So, my talk is articulated like that. I will give you an introduction about nanomedicine, ending up with magnetic fluid hyperthermia and how it is applied. Then I will discuss the challenges for clinical application. These are actually 3 different challenges, and I will end up with some concluding remarks. Nanotechnology, as you know, is the engineering and manufacturing of matter at an atomic or molecular level. The idea of nanotechnology has been around since it was coined by Richard Feynman, the famous Nobelist, since 1959. And he foresaw its use in the future in many different applications, and indeed nanotechnology is being used without perhaps even the consumer knowing in many different commercial and consumer products. In the area of medicine, the introduction of nanotechnology has become known under the umbrella of nanomedicine, and in this nanomedical field, people are trying to manufacture nanoparticles in a way that they can interact with the living matter, but at the size of the cell, or even at smaller sizes than the cell size. It hasn't been an easy path, the path to create 3D nanoparticles. In fact, people have created first 1D and 2D structures, as I will show you in the next slide, and then eventually they managed to do some inorganic, metallic, that is, nanoparticles in 3 dimensions. So we have started with multi-layer films, then with 2D ordered arrays, and finally we had the 3D nanoparticles that can take different shapes and forms. Now we are, by we I don't mean myself because I'm not a chemist or a chemical engineer, but my colleagues in the group, they are able to manufacture different sizes and shapes of nanoparticles, in particular magnetic nanoparticles. And you can have the classical ones, which are the spheres, and then you can have even stars or multipods. Multipods because they have a pod, comes from the Greek word pous, which means leg. So you can have nanoparticles with several legs protruding outside of them. What are these nanoparticles? Then nanoparticles can be considered as being spherical-like. They have a diameter, let's say this is a convention of less than 50 nanometers when they are naked, and yet they contain more than 10,000 up to 100,000 atoms. These atoms, I show you here a magnetic nanoparticle of different iron oxides. These atoms, they are mostly structured for metallic nanoparticles inside the lattice. Okay, this is a lattice. Physicists are aware of how the atoms in a metal, they are structured in space. And the lattice, inside this nanoparticle, in such a small dimension, you can have tens of thousands of these red or green dots, which are the atoms that construct your nanoparticle and the lattice. So now we have managed to create, or we can create, many different shapes and sizes of nanoparticles, but have we been able to push them through to medical applications? This was a quite recent review that shows how many of the nanomedicine applications in terms of drugs, and this doesn't include only metallic nanoparticles like the ones we're going to talk about today, that is magnetic nanoparticles, which are metallic, of course, but you can see also different nanostructures like nanocrystals, micelles, liposomes, etc., or polymeric nanoparticles. How many of them have been FDA approved? And if you take the orange color, which are the metallic nanoparticles, and these are the nanoparticles that are used, in fact, also in magnetic fluid hyperthermia, then you can see that there was a boom. Last decade and this decade, this has decreased a lot. And I can mention here some of the drugs that contain this kind of metallic iron oxide nanoparticles. And mostly, the first ones, they are used for supplying iron to anemic patients with a chronic kidney disease. So these are not used, although they are iron oxides, they are used mainly for drug delivery, for delivering iron to the patients. Then we had also some of these products that were used as contrast agents, and I can see from these that at least 2 of these products have already been removed, although they had taken FDA approval. They have been now removed from the market since many years, for reasons unknown most probably to most medical doctors and the nanomedicine community. But among these drugs that contain iron oxide, the most interesting is this one, Nanotherm, which is a trademark of Magforce. And this is the solution, or you say the dispersion, with iron oxide nanoparticles that is used in clinics for magnetic fluid hyperthermia. And this is not, of course, FDA approved, but it is EU approved. That happened in 2011, and gave a big boost to this magnetic fluid hyperthermia treatment. We have known magnetic hyperthermia for a long time now, since the 50s, but as I said, it only happened when the Nanotherm was approved for use in Europe, that the magnetic fluid hyperthermia took off as a treatment modality. How is this Nanotherm applied? How is magnetic fluid hyperthermia applied? You can see here the treatment of glioblastoma, in fact of recurrent glioblastoma. What the medical doctors do, they put catheters inside transcranially, inside the patient, and then instead of pushing inside the fluid, because that would mean that they hit on a lot of resistance, of mechanical resistance from the densely populated tumor, what they do is they retract the catheter, so you can see tracts, the blue color are tracts of the nanoparticles after they get inserted inside the tumor. And then they heat, and you can have temperature decrease even up to 50 degrees centigrade. I still find, after the review about recurrent glioblastoma that happened in 2017, I still find that the results of this study with Neurotherm, with magnetic fluid hyperthermia and irradiation, quite convincing that it is, I mean, if you look at the survival probability, the overall survival probability, you find that it is a very convincing solution for these patients. What do we want to achieve then when we insert this magnetic fluid, dispersion of the iron oxide nanoparticles inside the tumor? Of course, we want to achieve as much of the fluid as possible. This is not done once. You can see that you can have to implant the catheter and retract it several times in order to get some little quantity only of the liquid, so some mLs. And this actually could be improved somehow. If this could be improved somehow, so the availability of the magnetic fluid inside the tumor, it would lead to a better heating and to an increase in the temperature rise. In the temperature inside the tumor volume. Another thing that we know, so this is another application of the same fluid, but for prostate. Another thing we know is how much is the heating efficiency of these nanoparticles. So from this paper, we can see that the mean and the median values for the SCR, so the watts in per kilogram, that is actually left as a power deposited to the tissues from this application, from this clinical application, is around 120. So it would be nice if we could even increase further these SAR values and make the nanoparticles heat a little bit further. And this is the place where physicists together work with chemists to improve these values, as I will show you later. So in order to go from the experiment to the clinical application, we have to meet several points. And these are the challenges for the clinical application. First of all, we have to have quality assurance in the synthesis of nanoparticles. Then we have to make sure they are biocompatible. We have to characterize them. By characterization, always mean physical characterization, is what the physicists we do. And then the nanoparticles have to be administered somehow to the tumor. Until now, we have only local administration, transdermal or transcranial, but some people are working on the systemic administration. So you can have like an injection of a bolus with a magnetic fluid in the blood intravenously, and then somehow make the nanoparticles stay in the tumor and then hit there. And of course, a new area of application is how we create the magnetic field outside and how we apply it. Because I will tell you later, there is a problem with how much high we can go with the magnetic field. The higher we go, of course, the more SAR we have, the more heat is deposited. But there is a limitation to what we can do with the magnetic field. And in our lab, we're trying also on new ideas about the magnetic field application and focusing. So let's start with the quality assurance first, which is a big step towards clinical implementation. For synthesis, you can find in different textbooks, you can find several ways or several techniques to synthesize magnetic nanoparticles. Here I have like about 20 of them. And some of them, they are top-bottom. And some of them, they are top-bottom or top-down, and some of them are bottom-up. What do we mean by top-down or top-bottom methods? This is very, very easy to understand, because if you take, for example, iron rust from remains of iron or iron material, you can do milling, and with a milling device, you can break down the matter up to the nanoparticle range. But these nanoparticles, they have a big dispersion, so you cannot control their radius and you cannot control their physical characteristics. So this is a very brute way, of a very raw way to create your nanoparticles. And the other way is to synthesize them. In a chemical way, synthesize them from the different materials or the different substances that you can get. And this is what most people do. For example, you see here this technique, which is called nanoreactors microemulsions technique, where you can have two different inorganic compounds like chloric iron and bromide sodium, which come in microemulsions. And when you mix the microemulsions together, what happens is, because of entropy, because of thermodynamics, because of the Gibbs energy, the microcells, the microemulsions, the droplets, they come together. And as they come together, they create other bigger droplets, and you have a mixture of these inorganic compounds, and in the end, you have the creation of iron. And this iron then can be oxidized, but it's already in a very small size. This means, for example, that if you create how much of the lipid phase you have, compared to the hydro phase, to the water phase you have in your microemulsion, you can create iron or iron oxide nanoparticles that range in size, and you can even have like sizes of 8 nanometers ranging or up to 20 nanometers. The good thing about these techniques is that the nanoparticles you get not only have a controlled size, and as I will tell you later, size matters. They don't only have a controlled size, but they can have also a small dispersion. So the nanoparticles you create, they are around a median value of radius, and they have a very small dispersion around it. So another technique that we use in our lab is coprecipitation, where you can use different mixtures of ferric and ferrous salts of iron, and then you have an alkaline solution again, and you mix them together. But then, depending on various factors, like if you put first ferric instead of ferrous and so on, so even the mixing order of the different materials can lead to different nanoparticle sizes and to different dispersions of the nanoparticles. But anyway, this is what we do now, and we have tried several ways of mixing, of keeping the temperature and so on. And now we end up with very good nanoparticles. You can see here how it is. This is my PhD student, how Nikos then is making these nanoparticles. They come out from precipitation, they come out like a slime, this mud, okay? This is like black mud. Then you let it dry for a couple of days in your booth. And then what you do is you can mill it down to real nanoparticle powder. And of course, that you have to put, after that, you have to put it in an aqueous solution to be dispersed. So we can create magnetite, so iron oxide nanoparticles. Why is it so important everybody is trying to do iron oxides? Because iron oxides are the nanoparticles which have been, as I showed you before, cleared by the FDA. We know that these nanoparticles, they are biocompatible. And here, perhaps, because this is an educational day, we should discuss a little bit about biomaterials and different categories of biomaterials. So we have biotolerant materials. So this happens, for example, for PMMA-E or silicon and glass nanoparticles. And what happens there is that the body reacts by encapsulating them, and then they remain without any problem inside the body. Then you have bioinert materials, like the ones we have in passive implants. This is stainless steel, titanium, aluminum oxide, etc., which means that there is no interaction between these materials and the surrounding tissue. Unfortunately, we don't have any nanoparticles, or it's not true. It's difficult to create nanoparticles with these metals, and they don't have any magnetic properties anyway. Then we have bioactive materials where we know that these will interact with any bone, with hard or soft tissues, if they're placed in vivo, but magnetic nanoparticles do not fall into that category. Magnetic nanoparticles are biocompatible, and especially iron oxide nanoparticles, because they produce a specific and well-defined host response on the cells, which is not toxic. Okay, so that's what we mean biocompatible. It doesn't mean that they do not interact with the cells. They do interact with the cells. Because iron oxide nanoparticles, they interact with the cells through endocytosis, diffusion, or perhaps even through depolarization of the membrane. And sometimes when we have a lot of ions inside the cytoplasm, we might get disturbance in the functioning of the mitochondria or the Golgi system or anything else inside the cell because of the reactive oxygen species that's known to be produced because of these iron ions. So we know that up to a concentration or a dosage, the iron nanoparticles, they do interact with the cells, but without being toxic. Above some dose, they can be very toxic, and we can see that in viability of the nanoparticles. Because every time in the lab in Thessaloniki, we use a new nanoparticle, magnetic nanoparticle for testing its heating efficiency. What we do is also we try to figure out what is its concentration that would be non-toxic for the healthy or the cancerous cell line. So the nanoparticles we are dealing with, the iron oxides, they can be toxic but above some concentration in the tissues. And of course, their dimensions, they play a lot of role in the pharmacokinetics of these nanoparticles, which is a very challenging task now. I don't know that many people are working on the pharmacokinetics of nanoparticles, but what plays a role there is the size. So the nanoparticles are smaller than usual particles like we used to deal with before. This means that they could penetrate deeper inside the tissue, for example. Okay? Their surface area is larger compared to the volume area than before. This means they can be more reactive. So they are more chemically active than other particles, etc. And then the durability. We have seen, for example, that if you have nanoparticles that are secluded inside a lysosome, there is a physical change in the lattice because of the different pH of the cytoplasm compared to the lysosome here. So also we have to see how durable they are and what is their chemistry as they stay inside the organism. That's why we use some surface cover and we functionalize them so that we can change their biological properties. So what is the rule then? What is the process we try to meet? We can synthesize nanoparticles in water. That's fine. Water is a solvent which is biocompatible. So immediately we can functionalize them to interact in a specific way with the cells. Then we can have synthesis in an organic medium. And then when we have synthesis in an organic medium, we have to make sure that the nanoparticles that we have created, they can be also water dispersed. Because there are some organic media which are solvents and we cannot put inside the body, okay? Hexane or whatever. So what we have to do is we have to make nanoparticles that are always water dispersible, then we can functionalize them, and then we can put them inside the human body. I have to say that, and by functionalization, I mean that we put around the nanoparticles several different molecules, macromolecules like dextran, they are pegylated and so on, and this gives them a different biological function than the naked magnetic core, the naked nanoparticle. And when they have this function around them, this functionalized areas around them, they can interact with the cells in a different way, because when you have the nanoparticles naked inside your body, they will be removed by macrophages that are everywhere in your body, almost everywhere in your body, and especially in the liver with the Kupffer cells. What happens is that the naked nanoparticles, they get coated by proteins that are recognized by the Kupffer cells and they are removed from the bloodstream. This is this process of coating the nanoparticles with proteins is called opsonization. So perhaps sometimes we want the nanoparticles to be internalized, although it has been shown a long time now that it doesn't play a role for magnetic fluid hyperthermia whether the nanoparticles are inside the cytoplasm or in the interstitial space, so it doesn't matter very much for the heating. But sometimes we want to get them inside, and then we can do it in different ways. So we can, for example, promote the phagocytosis in different ways of the nanoparticles. I have to say that the synthesis, the mere synthesis, before we go to functionalization of the nanoparticles is only nowadays under standardization. So you can have different groups following the same recipe, because these are recipes for creating nanoparticles, and then end up with nanoparticles with different physical characteristics. So if you go to the microscope, to the TM, and you take a TM picture, although they have followed the same recipe, you don't get the same result in different labs. So ISO has created now a group, a working group, or like a technical committee, which will standardize the synthesis of nanoparticles. And we get also the same effect even from commercial manufacturers of nanoparticles. They have like specifications for them, but then when you get them and you characterize them physically in your lab, you might get different quantities or different properties from batch to batch. So the synthesis is a very important step for quality assurance if we want to have in the clinics repeatable treatments and kind of traceable treatments. Okay? Now, let's go about the characterization and the magnetism. You know, of course, that, okay, let's keep that because you can't see it, but you know, of course, that when you apply an external magnetic field H to your matter, to your material, then depending on what the magnetization, sorry, I forgot to tell you what magnetization is. Magnetization is the vector sum of the different spins you have in, not spins, you don't know what a spin is most probably, the medical doctors. Let's take it from the beginning. Let's assume that the atoms you have inside your lattice that I showed you before, they are little compasses, magnetic compasses. This means that if you put them inside a magnetic field, they will behave like small magnets, okay? But depending on how they orient themselves to that external field, then you have a different property of the material ranging from ferromagnetism, antiferromagnetism, paramagnetism, and so on, which I will show you later. So the total vector of all these small magnets is called magnetization of the material, okay? So let's see if we apply an external magnetic field, how the magnetization changes, okay? So in the beginning it changes like that, and it is true that when you reverse the magnetic field, the magnetization follows a different path. And for ferromagnetism, this makes what we call the hysteresis loop. So in ferromagnetism, because of the anisotropy energy, I will not come into many, magnetocrystalline, energy, which I will not come in many details, but because of that, when we apply the external field and we reverse it, we have a different behavior of the total vector of all the different magnets inside your material. The only cases where we have the same effect if we increase the magnetic field or we reverse it are these green and red lines, which is diamagnetism and paramagnetism, okay? And there is another kind of materials which actually come from the ferromagnetism, and they are called super paramagnetic materials, where we don't have a hysteresis loop. We don't have this hysteresis loop, but this loop is very small. What we call, we say that the coercive field, because the coercive field you can see already on the screen here, the coercive field of these materials is very small. But we'll talk about that later. So, depending on how these materials behave when that's the bottom line. Depending on how these materials behave when we have them inside an alternating external magnetic fields, we have different categories of materials, okay? Of interest for magnetic fluid hyperthermia are the super paramagnetic and the ferromagnetic materials. I will not go into magnetic theory. I will just show you this one because it's important. Inside each one of these magnetic materials, we can have what we call magnetic walls. Magnetic walls are the areas or the walls that separate areas inside your nanoparticle where the total magnetization can be different. You can see, for example, that if you have a single domain, as we say, and you don't have any magnetic walls, this is on the left side on the top for your magnetic nanoparticle. This means that all the magnets, they can easily orient towards the magnetic, the external magnetic field, and they create only one total magnetization. But if you make more or larger nanoparticles, what we have is that some of the magnets, they orient themselves in one direction and some to the other direction. And this is happening, again, due to thermodynamics. This is energy preservation. You can see, for example, that the magnetic loops, the magnetic current, okay, or the paths outside, they are larger when you have a single domain and no walls. They are smaller when you have more domains and you have walls in between them. And this helps us keep the total internal energy of your nanoparticle law, which is one of the principles of physics. Okay? So what we know is that as the nanoparticle becomes larger and larger and larger, the magnetic dipoles, the small compasses you have here, okay, they can behave different from each other when the nanoparticle is very small. They behave different from each other when the nanoparticle is small, so independently. Then as the particle diameter increases, this is the ferromagnetic area, you have one single magnetic dipole, okay, so all of them, they are on the same direction, on the same page. And when you have a nanoparticle that becomes even larger, then in between the nanoparticle, you can have magnetic walls and you have different domains where you have the small magnets oriented at different directions together. Okay? So, do we know the radii at where the magnetization or the magnetic behavior of the nanoparticle changes? Yes, we know. So, there are some radii where you have superparamagnetic behavior. In this behavior, every dipole, every compass behaves on its own in the atom. Then if you go from right to left, you have single domain, you don't have any magnetic walls if the nanoparticle becomes larger. So all the dipoles, all the small compasses, they behave as one, okay? And then when you have a larger nanoparticle, you can have different of these single domains inside your nanoparticle and also some magnetic walls forming inside your nanoparticle. The first regime is the superparamagnetic regime, the one on the right. The other two are the ferromagnetic regimes for your nanoparticles. And you can see here what is, depending on the nanoparticle diameter, for different nanoparticles and for different metals, you can see how what is the radius where this happens, okay? Now, what it happens then is that the iron oxide nanoparticles below 20 nanometers, about below 20 nanometers, they are superparamagnetic, so the spins, they behave different from each other. Then, as we increase the particle size, they become ferromagnetic, and we have a different way of depositing their energy. And when they become larger, and you have several domains, as I showed, inside the nanoparticles, then the energy they can leave to the space is smaller because their hysteresis loop here, the hysteresis loop becomes smaller because the coercive field becomes smaller here. So there are two ways for giving energy to the environment for the magnetic nanoparticles. The first way is for the very small nanoparticles, the superparamagnetic ones. You can see that on the top, where we can see that each nanoparticle spin can change the direction, but this leaves energy to the space around. This is called Snell relaxation. Then we can have in the ferromagnetic regime, we can have the hysteresis loop that I showed you before, and the energy that is left to the environment of the nanoparticles as the magnetic field changes direction is the area of this hysteresis loop. Okay? If the nanoparticle diameter becomes larger and larger and larger, this hysteresis loop becomes narrower, 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 and we cannot get much energy from the inversion of the magnetization inside the nanoparticle. Okay? So there is a nanoparticle diameter where we can get the maximum of this ferromagnetic behavior of the nanoparticle, and then we have a fall of the energy that it can give to the surrounding environment. Of course, we can have also Brownian movement. By Brownian movement, we mean that where the Horn nanoparticle changes, and then due to the viscous environment where it finds itself, we can have also, because of friction, energy release from the nanoparticle. But what we get usually is either this Snell relaxation for the very, very small superparamagnetic nanoparticles, so this is that mechanism, or we can get the ferromagnetic loop that gives us the energy to the environment. Okay, how do we characterize the nanoparticle heating efficiency. We do that in the lab, and we can do it with cells inside the solution or without. And we use a coil, okay? We put the sample in there, and we use a thermometer. In this case, the thermometer is, of course, an optical fiber, okay? We use also infrared cameras to see the heating of the coil and also the heating of the sample. You can see here when the coil is conducting current, so that creates an AC field, an AC magnetic field along its axis. You can see the increase of the temperature because of the release of energy from nanoparticles. And I repeat here, perhaps will tire you, that there are two ways of releasing energy, either with an air relaxation or with loop hysteresis. Okay, so they can be either super paramagnetic or they can be ferromagnetic, the iron oxide nanoparticles. And then we measure the temperature increase, then we turn off the current, and you can see the drop off from the temperature. Why do we measure always? We always measure in the lab both the increase and the fall of the temperature. Why? Because as the previous speaker showed for HIFU, that was very interesting the way they do their control of the heating, where they heat. Here you have the same idea. When you have heating of your sample with the nanoparticles, you have also a heat exchange with the environment, usually. So this means that after some time, what you measure will not be the temperature rise in an adiabatic system. This is not a closed system, it's not an adiabatic one. You have heat exchange. So what we do is we switch off and we measure what heat exchange there is when we switch off, and that we subtract from the measurement and we calculate what would be the actual adiabatic heating of the sample. And from that, of course, we can calculate the specific loss power, which is the heating efficiency of the nanoparticle. This is how many watts per gram of ferromagnetic materials are created inside our volume. So there is one point I need to make. In the literature, you find this value also as SAR, specific absorption rate. I have to distinguish, and this is a personal view, but I have to say it to be politically correct, that SAR is different from SLP. SLP is, although they have the same physical dimensions, they are both watts per mass, power per mass. SLP actually shows the heating efficiency of your nanoparticles per gram of heating, let's say, material. SAR shows how much of this energy is deposited to the surrounding tissue. So they are two different, to me, they are two distinguished quantities. But anyway, in the literature, you can find that the SLP is also known as SAR, specific absorption rate. And you can see that here. This is a very interesting paper where they took what was measured in the literature from 50 different nanoparticle systems, and they corrected for this line, for the adiabatic system, and you can see that the range of the reported to the actual SAR after the correct can be up to 2, to a value of 2 or half. This means that we have 100% uncertainty in the measurement of the SLP in some of the systems that there are around in the laboratories all over the world. So what we do is we always do the heating, the cooling, and of course we have the heating and the cooling also for the solvent alone without the nanoparticles, because this also gives us an information of the energy that is transferred from the coil to your sample. Another issue that needs to be taken into account is when you do your simulations, these are simulations with COMSOL, with numerical simulations, you have to be sure what sort of physics there are behind your heating. For example, if you have a 10 nanometer iron oxide nanoparticles, this is the blue line, you can see that there is no hysteresis here. If we use the literature values for the power that is deposited inside your medium for super paramagnetic nanoparticles, okay, you can see that you have a very nice, let's say, agreement between your experimental value, which is measured with the optical fiber, and your numerical results. But if you use that, and your nanoparticles are actually ferromagnetic nanoparticles, they are 40 nanometers, you lag behind in the energy that is transferred to your sample, and then you can have to use the ferromagnetic power calculation to have a matching between your numerics and your experiment. So we have to be sure when we're doing numerical simulations or when we're doing treatment planning further in the clinics, what sort of behavior our nanoparticles have. Are they in the superparamagnetic regime or are they in the ferromagnetic regime? Because the power they deposit to the tissues, to the surrounding tissues, has to be calculated in a different way. Okay? Of course, the shape of the nanoparticles plays a role. This is a result from the Harry Sinkrat group in University of South Florida, where they have created also spheres, and because, they have created cubes, and because the anisotropy of the cube is higher than the anisotropy of a sphere, actually the sphere doesn't have any anisotropy, but the cube is an anisotropic shape, then you have a higher SLP for the same magnetic field. And of course, you can increase the anisotropy if you make the nanoparticles build chains, then you have high anisotropy. And then this is from a publication of ours, of our group. And you can show here that if they are random-oriented, the nanoparticles, compared to when they are chained, they form anisotropic structures, you can have a higher temperature rise because the SLP of these nanoparticles is higher. Now, with what sort of accuracy or certainty do we measure the heating efficiency of nanoparticles? We can simulate. First of all, we see that inside any heating system where we want to measure the SLP of the nanoparticles, the magnetic field is not uniform. You don't have a uniform magnetic field, so you have to know where you're measuring and what your magnetic field is at this point, and that you can do only by simulations or by measuring the magnetic field when the coil is on. The other thing is, where do you measure? Do you measure in the middle of the vial? Do you measure on the end points? So you can see that for different positions inside the very small vial, which contains only 1 milliliter of a solute, of a dispersion, you have different temperature rises inside your vial. So you have to know also where you are measuring. And of course, also the vial plays a role. And this is something that came to a surprise to us. These are all results that have been recently published last month, I believe, yes, in collaboration with a group from Rotterdam. And you can see that even the vial plays a role because it has to do with the precipitation of the nanoparticles inside of the vial and the formation of currents, of mass currents, mass transfer inside the vial, depending on its shape. Then, this goes about quality assurance and how we synthesize, we make them biocompatible, and you characterize the physical properties. I will very fast move now to the administration. Local administration has already been known since 30 years now, when Kobayashi started with iron platinum seeds, thermal seeds, and they used to put them, of course, by surgical procedures inside the patient that they treated. But some people say that we should take advantage of the enhanced permeability and retention effect that happens at the tumors, where, as you know, the blood vessels, they don't have such nice walls, and then you have the nanoparticles coming at larger quantities to the tissue, so they extravasate more inside the tumor than they do in healthy tissues. And some people think that we should even help them get out of the bloodstream with external magnets by attracting them. But what we have to take into account, this is a very recent paper, a very good one. It's a kind of a review that shows what is the effect of the different 4 S's of nanoparticles flowing inside your blood vessels. And of course, depending on the size, shape, and stiffness, so if they are, let's say, stiff like naked iron nanoparticles, or they are even soft like they are polymer nanoparticles, there are differences on how they flow inside your blood vessels. And you can see, for example, that the spheres
This doesn't show very well. They have even shown in vivo results, but I will show you this one. You can see, for example, that the spheres, they marginate more. So we know that already from the erythrocytes, that the erythrocytes, they stay inside the center of the vessel as they flow, right? So that's why when you take a hematocrit at the limbs, it's different from the hematocrit you have in your trunk. Okay? So this happens also with the other nanoparticles. You can see that depending on the shape of your nanoparticle, they can flow next to the walls, so they can extravasate easier, or they can flow in the middle of your blood vessel. So the thing is that if you are a simple physicist, you would say, okay, physics shows that if you have anisotropy in your nanoparticles, you have a higher SAR. So I would favor anisotropic nanoparticles. But the biologists would say, hey, what's happening with anisotropic or with prolate or oblate nanoparticles when they flow? And if I want to give them to the patient in a systemic way, we have to take into account the different way that, for example, prolates, they flow in the middle. Instead of spheres, they flow on the margins of the blood vessel. So we have somehow to counterbalance these different effects. Or we can attract the nanoparticles, perhaps. And here you can see the physics behind attracting nanoparticles. In order to attract the nanoparticles, you have to have a non-uniform and inhomogeneous field, because you have to have a gradient of a magnetic field. This is the lower equation. And you can do that, of course, with a magnet. These are some calculations we have made. And we have seen in the literature with one magnet you cannot achieve a lot. With two magnets, which is the second figure here, although the mathematics, they are getting quite complicated on the magnetic field inside the vessel, okay, you can see that the force is enough to take away most of the nanoparticles. And by taking away, we mean to bring them to the wall, and from the wall they will extravasate to the interstitial space. But, there is a big but, the problem is that the distance you have between the magnet and the vessel is quite small. So it is about 1 centimeter above your body or above your vessel, which makes it only natural for the tumors you see in the literature. So for superficial kind of tumors in rats and animal models. So in this situation, yes, they have attracted with magnetic field, they have attracted, and with the nanoparticles, we have attracted a lot more nanoparticles in the tumor, but this was quite a superficial tumor. I don't believe we can do that in tumors where we have now the clinical application, like in glioblastoma or with prostate, although it would be a challenge to use magnetic fields that already exist, perhaps from MRI, because it's also an idea, to navigate the nanoparticles inside your body. Okay, this is also something else. You can see they are also very superficial blood vessels, and they can have managed to attract with a magnetic field about 10 times more nanoparticles than without the magnetic field. The last part is about magnetic field application. Those who work in magnetic fluid hyperthermia, they know that there is one limitation in applying an external magnetic field to your body of alternating frequency, and this is the Brezovich or the Atkinson-Brezovich criterion. This tells us that the amplitude of the external magnetic field multiplied by its frequency has to be below a threshold, and this threshold is where we have either pain or we have, because of the eddy currents forming, so as you know, all our tissues, even healthy tissue, is conductive material for electromagnetics. This means that we have ions that flow, and we have conducting currents. So eddy currents can form if we found ourselves inside a changing magnetic field. And this would give rise, the external magnetic field, would give rise also to eddy currents in the healthy tissues. Not only in the tissues which are flooded with magnetic nanoparticles, but also in the surrounding tissues, making them hotter or even creating pain because of the nerve stimulation inside the patient. So there is this criterion, and people from the States, they thought, okay, let's try to minimize the effect of this eddy currents, how by moving the external coil, so if you have the nanoparticles here, okay, if you have the nanoparticles here in this volume which is black, and you have a coil, this is the phantom, what you see in color is the phantom, which is of conductive material. You have a coil from below. You can see here on the top, on the bottom right, you can see the setup. And this coil is conducted by, is flown by current, okay? And what you can see on the left, on the bottom left side, is the eddy currents just above the coil spirals, and you can see that you have heating also there. You have heating at the phantom in the healthy part, not where your nanoparticles are. How can we reduce this heating? So they thought, let's move the coil. So if you have like a rotation or a translation of the coil, what you do is you smooth out these high values of heating, so you keep the magnetic field, you keep the nanoparticles inside the magnetic field, but the eddy currents, they get dispersed inside your healthy tissue and they don't heat up the healthy tissue. So this is one way of taking away the Brezovich criterion, and it's something that perhaps people can use in the clinics to apply the magnetic field to the patients that are administered with nanoparticles. The other setup that we're trying in our lab is focused hyperthermia. So instead of having only an external alternating magnetic field, we have also a static magnetic field. And if you have a static magnetic field, what it will do, it will make your compasses stabilize on this, they direct themselves and they stabilize on this external magnetic field, and they don't rotate with the alternating external magnetic field. But they rotate only where your static field is zero. That's what we call the field-free zone. And you can see here already with 4 magnetic permanent magnets, we have like a field-free area which is in the middle. And when we measure the SLP in this area, it is the highest. But when we measure it everywhere else where the nanoparticles, they are fixed because of the external static field, the SLP is very low. These are the red areas as you see here. Okay? And we have tried that with nanoparticles inside agarose gel, and it worked very nicely. We're trying to publish that now. So, to conclude, first of all, I have to say that in nanoparticles, size matters. Why does size matter? Because if we have smaller nanoparticles, and we inject them in the body, their plasma life is very small, they will get excreted by the kidneys very fast. If they become very large, okay, then they are better for hyperthermia. But if they become even larger, they get opsonized by the body, and they get removed again by the liver. This is for systemic administration. So what we can do is, with small nanoparticles, we do have best tumor penetration, because the smaller the size, the more the particle diffuses inside the tissue. But what we need are iron oxide particles, which are stealth. They're not picked up by our endoreticular system to be excreted, and we want to keep them, to keep them in the ferromagnetic regime, not in the superparamagnetic, just to make them heat a lot more because they have this size. And then, not only size matters, but I have shown that also for the systemic application in clinical practice, the shape also would matter, because they flow, they circulate in a different way inside our blood vessels, but also the heating efficiency changes. The more anisotropic they become, the more they heat, the nanoparticles. Then it appears that for the moment we have this challenge, but the local administration seems to be the most realistic choice for magnetic fluid hyperthermia. As I have shown you, we measure the SLP, the heating efficiency of the nanoparticles, or I hope that I have shown you, with a lot of uncertainty, which needs to be standardized. So not only the synthesis, but the International Standardization Organization should do also something about measurement of the heating efficiency of the nanoparticles. And there are several options for increasing the external applied magnetic field or reducing its effect.
For example, bifocusing is something we try in our lab in vitro and with agarose phantoms. So I would like to thank you for your attention, and I would like to thank also the group from the Aristotle University of Thessaloniki Department of Physics. It's called Magna Carta because of it's an acronym, magnetic characterization. And last week we were very happy to accommodate in our lab Harry Srinkath. People working in magnetic fluid hyperthermia are all aware of Harry, because Harry this year is the IEEE Distinguished Lecturer with the aim to promote magnetic fluid hyperthermia and the effect of anisotropy on magnetic nanoparticles. And we were very happy that he was traveling in Europe and he gave a lecture also, and he came and we discussed some of our projects in our lab. Thank you very much.